Yeah, I guess so. Well, we can make it due Thursday. I mean, all right. Kyle likes for the chapter 13 homework to be due next Thursday.
I like for it to be done this time.
He's not actually in the class. He just got through his surgery. He's probably still on his meds. And don't know if it's
All right, guys. So this problem says find the magnitude of. Okay, guys.
This is number 36.
26 looks like. Find the magnitude of the tensions in each supporting cable shown below. In each case, the weight of the suspended body is 100 newtons. So this guy is 100 newtons. Okay, and the masses of the cables are negligible. All right, now I'm not going to do all four. These three are similar. This is a little messy, but pick one of these guys and then I'll do that one.
The second one.
No, we'll do that, but pick one of these guys. Second one. Maybe this one, that angle, this is more complicated than that. Those angles are equal, so that's easier. So we'll do these two. Okay. Okay, guys, so now again, in all these problems, this is static equilibrium. Hey, guys, quiet. So in all these problems, what you want to do is you want to pick a point that is at rest. So for instance, if you look at this knot, that knot is at rest. That means all the forces acting on the knot must add up to 0. Okay, and since this is a point, all you need is this condition for equilibrium. So in this problem, we are not using this condition. You need to use this condition as well when the object is an extended object. Right now our object is a point object, so all we need is this condition. Okay, so we are doing part C. This angle is 60 degrees, 45 degrees, and this is 100 Newton. We'll call this tension T1, T2, T3. Okay, and you can see that T3 equal to 100 newtons. Okay. All right. And in all these problems, I will draw my x and y axis like that. X axis will be horizontal and y axis will be like that. Okay. So you're considering this knot. So T1 plus T2 plus T3 must equal 0. Okay. All right. Now, so there's T1. See, T3 has only a y component. So the x component of T1 must balance the x component of T2. And the y components of T1 and T2 should equal T3. Okay, so that's what we'll do. So let's look at the x components. So in this problem, this angle is 60 degrees, this angle is 45 degrees. So minus T1 cosine 60 plus T2 cosine 45 is 0. So minus T1 cosine 60 plus T2 cosine 45 equal to 0. Where in this equation, it's the magnitudes of T1 and T2 I've written. Okay. So T1 is equal to cosine 45 divided by So the x components of the forces tell us T2 is about 40% greater than, T1 is 40% greater than T2. Okay, so you see, the more vertical the rope, the greater the load it's bearing. Okay. All right, now let's look at the y component of the forces. The y component of the forces, you look, T1, the y component of T1 and T2 are balancing T3. Okay, so T1 sine 60 plus T2 sine 45 minus T3 equal to 0. And remember, T3 was 100 newtons. So T1 sine 60 and now to solve this, what you can do is you can substitute this information in there. Okay, so T1 is 1.41 T2 times sine 60 plus T2 sine 45 equal to 100. So T2 is 51.8 newtons and T1 is 1.41 times 51.8 newtons, which is equal to okay, so T1 is 73 newtons. Yeah. So again, the tension, the load being borne is 100 newtons. Okay, and this rope has to bear a 73 newton tension, and this has to bear a 52 newton tension. 52 newton. Okay, so the advantage of this configuration is the following. Let's say you want to hang a 1,000-pound object and you don't have ropes that can bear 1,000 pounds. So you tie ropes at an angle to the object, and now you're able to hang a heavy object with a weak rope. That's the point. Okay. All right. Any questions before we move on to the slightly more complicated one? Yep.
But wouldn't both those ropes, if they were hung directly, have less force on them than if they were?
Okay. So what our friend here is saying is,
Because otherwise it would be 50 newtons each.
yeah, that would be 15 newtons each. So yeah, I guess so. This is just aesthetics. Okay. Okay. All right, so we're going to do this problem. Now we're going to apply this to these three knots. We'll apply this knot is at rest, this knot is at rest, this knot is at rest. Okay, so T1, T2, T3 is equal to 0. I guess we'll call that T5, even though this problem is symmetric. So T1 will equal to this tension. Okay, and I'm just going to assume that. T3 will be equal to that. So really what you're solving for is 4 unknowns. 1, 2, 3, 4. Okay. And it's really 3 unknowns because T4 is equal to 100 newtons. That's easy. Okay. So you guys understand that? All right. So this is C, that's D. Okay. So I'll write this fairly quickly, okay? Okay, again, our x and y axes are like that. And we'll call this knot 1 and we'll call this knot 2. Okay. So T4 equal to 100 newtons. And that angle is 60 degrees, so this angle is 60 degrees. This angle is 60 degrees. All right, so we just look at the y component. The x components are balanced. The x component of this balances the x component of that. Okay. So T3 sine 60 plus T3 sine 60. That's the y component of this guy, and the y component of this guy is balancing T4. Minus T4 is equal to 0. Okay. So 2 T3 sine 60 is equal to 100. T3 equal to 50 divided by sine 60. $57.7 newtons. All right, so we have T4 and T3. Now let's move to knot 2. We'll move to knot 2 and we'll solve for T1 and T2. Okay. And let's look at the x components. Again, this angle is 45 degrees. Okay. All right, let's look at the x components. Minus T1 cosine 45 plus T2 plus T3 cosine 60 is equal to 0. Everybody see that? So this guy has an x component, that guy has an x component, and this guy has an x component. Okay. We've solved for T3, so all right. Well, we'll just T3 is 57.7. Okay, so let me into cosine 28.9. So minus T1 cosine 45. Okay, so that's what this works out to. This guy, T3 is 57.7, that times that is this. Bring this to the other side, that becomes positive, and bring that to the other side, that becomes negative. Okay, so that's what the x component of the equation is telling you. So here you have two unknowns, and so you need a second equation, and the y component will give you the second equation. Y component of the forces will give you a second equation. Okay, so let's look at the y components. And from the diagram, this y component, this guy doesn't have a y component. This y component is balancing this y component. Okay, so T1 sine 45 is minus T3 sine 60 is equal to 0. Okay. And T3 is 57.7. Yep.
With two T1 sine of 45 minus 100 newtons be a possible solution for T1.
I'm sorry?
So with both the T1 sine, the T1 sine 45 times 2, would that equal to
100 newtons. That would also equal. So what Kyle just said is the following. Good job. Okay, so here's another thing you want to notice. This is what Kyle did. Okay, these guys are all massless. They tell you that. Okay. What does this whole thing weigh? 100 newtons. Okay. And so this y component and this y component is balancing the 100 newtons. So what he's saying is T1 sine 45, this is 45, plus T1 sine 45 equal to 100 newtons. So T1 should equal 100 divided by 2 sine 45, which is 50 divided by sine 45, which is again 70.7 newtons. And let's make sure that this is a cross check. And let's, what did we get for T1? Yeah, 70 point. Yeah. All right, we still have to calculate T2. What is T2? Okay, 28.9 equal to, so we'll use this equation, 28.9 equal to 0.71 T1 minus T2. So T2 is equal to 0.71 T1 minus 28.9, and that's equal to 21.3 newtons. All right, so let's go back to the diagram. Okay, in all these problems, These are all static equilibrium problems. And what you're doing is you're identifying an object that is at rest. So in most cases, these knots that are at rest. And then all you do is use this equation. Look at all the forces acting on that knot, and they should all add up to 0. And that's what you're doing. Yeah? Now, like I said, these two equations will turn into an entire course for you guys, a junior or a senior level course, statics. Okay. So when you're considering a point object, that's the only equation you need to consider. But when the forces are acting on an extended object, you need to consider the torques of those forces should also add up to 0. Okay. So that's what you'll be doing. And of course, you are setting up as many equations as you have unknowns. And between those two equations, if you consider if the problem is a 3-dimensional problem, you'll end up having 6 equations. Okay? And so you can solve for up to 6 unknowns.